How's it going? So I'm behind on everything this week. I will try and get your homework graded by tonight. No promises. I think I should be able to though, which means of course I won't physically hand it back to you. I'll just scan it and upload it like I do with everyone else that doesn't physically come to class. What else? First exam is next Friday, right? Can confirm, yeah. So that'll cover everything through today. We should finish 3.2 today. Really just have 2 theorems to prove, and we might start on 3.3. We'll see how the class goes. But that'll be everything. And I think I want to assign a short homework from this section. Maybe just 2 problems or something. And since this is on the exam, I think what I'll do is I'll bump up the due date. I'll make it due next Wednesday. But again, it'll be short. It'll be half the length of regular homework. And I just want to do that so you'll sort of have done some 3.2 stuff and seen at least my solutions before the exam happens. So I think that's what I'm going to go with, but I'll post an announcement on Canvas tonight or tomorrow sometime. But anyway, here's our next theorem. Very familiar theorem, again from Geometry 1, which is a point is on the perpendicular bisector of a line segment if and only if it's equidistant from the endpoints. And once again, it should be familiar to you, but the point is that we can prove this without using any sort of parallel postulate, so it's true in neutral geometry. It's an if and only if statement, so there's 2 directions. Let's just do one. Let's do the backwards direction. So backwards direction is if it's equidistant, then let's prove it's on the perpendicular bisector. So suppose a point P is equidistant from the endpoints A and B of the line segment AB. All right, so we'll draw a picture here. We've got our line segment, AB, and I've got a point P that's equidistant from both of them. So that means that line segment AP is congruent to line segment BP. All right, so hence, what that says precisely is that AB is congruent to BP. Again, being careful about my notation here. When I put the bar, I'm talking about the line itself, so I don't want to say the line is equal, because they're not equal, but they are congruent. They have the same length. If I left the bar off the top, I would just say AP is equal to BP, because those are 2 numbers. What can I say? So the bisector of angle APB must do what? Well, in comes the crossbar theorem, right? If I draw in the bisector of angle APB, that has to intersect side AB at a point, right? At some point between A and B. So must intersect side AB at a point, we'll call this point T. So at a point T, such that A, then T, then B on that line by the crossbar theorem. What do we do now? Well, now we can invoke one of our postulates, the SAS postulate, right? Because we've already assumed that those 2 sides are the same length. Of course, these 2 sides are the same length because they're literally the same side. And this is an angle bisector, so those 2 angles are the same. So by SAS, it follows that these two triangles that we have, triangle APT is congruent to triangle triangle what? BPT. Yeah. Triangle BPT. Sure, I like this, but we'll see how this goes. So it follows that APT is congruent to BPT, and so therefore, so AT and BT are congruent as well. What does that mean? Well, since these are the same length, then T is the bisector of this side, AB, right? So AT is congruent to BT, and therefore, this thing we've drawn, PT, is the bisector of AB. So yeah, sorry, I lost track there of just where we were going, what we were trying to do. But what do we start with? We start with P is equidistant from A and B. We drew in this angle bisector of angle APB. And what I'm hoping to do is I'm hoping to show that this angle bisector is indeed the perpendicular bisector of AB. What we've shown so far is that because these two things have to be the same length, this is a bisector of side AB, but I need to show it's a perpendicular bisector. So the last thing I need to do is show that these are right angles, right? So also, what else do we have? Angle PAT, I believe. Oh, no, we've got ATP, yeah, the right angle. Angle ATP must be congruent to angle BTP. Why does that follow? Well, that follows because they're supplementary, they form a straight line, and they're equal to each other, right? So they're congruent, and because they are supplementary as well, it follows that both are right angles. All right, they're congruent by SAS. They're congruent by SAS, but because they're congruent and supplementary, because they're congruent and add up to 180, they must be right angles. So therefore, we're done. So the result follows. I don't like anything like this. So that is PT perpendicular bisector of AB. And so there's two things you have to do, right? To show it's a perpendicular bisector, one, you have to show it bisects a side, which we did by establishing SAS. These two sides are the same length, therefore it is right down the middle. And by SAS, these two angles are congruent. Well, looking at them, they are also supplementary. So if they're equal and add to 180, then they must be right angles. So this is a perpendicular bisector. We then, of course, have the opposite direction, the forward direction. If P is on the perpendicular bisector, then it's equidistant. So if it's on the perpendicular bisector, then these two sides are the same length. I will either officially assign this for homework or just leave it to you as a homework exercise, but it's not any harder of a proof. And I think literally we've done exactly this in Geometry 1 at some point. All right, moving on then, another big theorem. This is the exterior angle theorem, or sometimes called the weak exterior angle theorem, because the stronger version is only true in Euclidean geometry. It's so nice before the board gets all messed up. Anyway, this is, we need a quick definition first. We'll define exterior angles. So, any angle that is both supplementary and adjacent to an angle of a triangle is called an exterior angle. Called an exterior angle of the triangle. Again, I'm sure you already know this definition, but I do want this class to sort of be able to stand alone. So what I mean by this is, here's a triangle, there's an interior angle, and the exterior angle has to be supplementary to this guy and adjacent to it. So there's an exterior angle. Here's another one. And notice, by the way, those two exterior angles are the same, right? Because they're vertical angles. So here's the theorem. And this is the exterior angle theorem. And sometimes called the weak exterior angle theorem. What does this theorem say? Do you know? Do you remember? What's true about exterior angles of a triangle? Well, you might say they're equal in sum to the other two angles, right? You might say, since these two angles have to add to 180, well then this angle must be the sum of those two angles, right? Turns out that's a strong exterior angle theorem, right? Because that assumes that the angle sum of a triangle is 180 degrees. So the weak version just says that the exterior angle is bigger than the other two individually. each exterior angle of a triangle is greater in measure than either of the non-adjacent, which I don't think needs to be hyphenated. I think non-adjacent can be one word. But anyway, non-adjacent interior angles of the triangle. All right, so once again, this is just saying if I look at an exterior angle, that has to be bigger in size, bigger in measure than either of the non-adjacent angles. This is one of these clues that Euclid recognized that his fifth postulate was weird, right? This parallel postulate, it's sort of because he proves this first. He proves this theorem, and then he goes on to prove the stronger version, which is that this angle is equal in sum to the sum of, or equal in measure to the sum of the other two non-adjacent angles. But he proves this first, and he proves this first obviously without using the fifth postulate, because it's true in neutral geometry, we don't need parallel postulates. And then he proves the stronger version about equaling 180 degrees, or equaling the sum of the other two ones, because you do need the parallel postulate there. And it gives us a little bit of insight into the fact that he realized that the fifth postulate was strange, and he didn't want to invoke it if he didn't have to. So I'll only prove one case. I think we'll prove that this angle has to be bigger than this one. And I'll leave the other one as an exercise. Proof. Let's see. We'll just draw some stuff first. Consider a triangle ABC, and let D be a point on side AB. Oops, we'll extend AB such that A, then B, then D. All right, so we've got this triangle. We've got this triangle A, B, C, and I've extended side AB, and I've chosen this point D on there. What do I want to do? So I want to come in and look at this angle, and I want to show that angle CBD is bigger in measure than, well, both of these, but we'll just do one, bigger in measure than angle ACM, or ACB. So we want to show that measure of angle CBD is larger than the measure of angle, what is it, BAC, and the measure of angle ACB. And I'm pretty sure the direction we're going with this proof is we'll just do this one. We do this one only. The other case is similar. All right, so what are we going to do? Well, here's the trick. So let's let E be the midpoint of side BC. So I'm going to come into BC and choose the midpoint. Why am I allowed to do that? Well, we already have a theorem that says that every line segment has a unique midpoint, right? So choose the unique midpoint. And I'm going to draw a ray in here. Okay, so, and find F on this extended ray AE such that A, then E, then F, and so that F is the same distance away from E as A is. Okay, so, and so that AE is congruent to EF. So let's see, I'm going to extend this ray, we'll draw this ray out, and we'll choose F. Oh, that's about right. So that F is the same distance from E as A is. What am I trying to do here? I'm going to build, basically, I'm going to build a copy of this angle inside of this angle here to show that it's smaller. How am I going to do that? Well, I'm building a congruent triangle. So by SAS, we have that triangle ACE is congruent to triangle BEF. Do you believe that? So now I have all these points drawn. Let's just complete this triangle. Do you believe that this triangle here, ACE, is congruent to this triangle? I'm claiming it follows by SAS. What do I have? Well, I have that this side is the same length as this side. That's how E was chosen. E was chosen to be the midpoint. So those two sides are the same length. We constructed F. We chose F so that these two sides are the same length. And of course, we have two vertical angles here, right? Those two angles are congruent. So it does indeed follow by SAS. I suppose I'm not writing down all the details. Usually I would write, it follows because this is equal to this is equal to this, but it's clear by the picture. By SAS, these are congruent. But therefore, I think what I want to claim now is that these two angles that must be congruent. ACE, those two angles are congruent. So hence, we'll put a comma here. Hence, angle ACE is congruent to angle EBF. Okay, so we have congruence of these two angles. The last thing I need to conclude is that this angle, which is this angle, must be smaller than this bigger one. And from the picture, it's totally clear, but it's subtle. It follows from the parallel, or not the parallel, the plane separation axiom, that F has to lie sort of inside this angle. How do I know that? Well, I know because it's sort of on the same side of this line and this line, that it must be sort of interior, and therefore this angle is smaller than this bigger exterior angle. So it's a little bit subtle, but finally, observe that this point F is interior to angle CBD, So it follows that the measure of angle CBD is bigger than the measure of angle EBF. But we've already established that the measure of angle EBF is the same as measure of angle ACB. To be fair, before we called it ACE, but obviously ACE and ACB are the same angle. So measure of angle ACB, which is precisely what we wanted to do. Yeah, the other case, the measure of angle BAC case is, I'll call it similar. This is what the textbook does. It says this is similar, and I'll probably assign it for homework if I can. But I don't like that they call it similar, because I wouldn't necessarily say that it is. Not in a direct sense. So I'll give you a hint. If I do assign this for homework, obviously you're going to do sort of the same tricks, right? But the problem is, how do you build this angle in here? And the answer is, I don't see a way to do it. Not using this line. So the trick is, what do? We drew a line out from A, cutting through here. I believe what you'd want to do is you want to draw a line out from C, cutting through the midpoint here. And what you're going to do is you're going to build a copy of this angle, not in this exterior angle, but you're going to build it in here instead. And that works totally fine, because this exterior angle is the same as this exterior angle, because they're vertical. So it is similar in the sense of you're doing the same trick, but you're sort of reversing the picture. You're cutting through this side instead. Otherwise, it should be almost exactly the same. Any questions? All right. We have long enough, so why not get started on the next section? I don't want to do a whole lot before the exam, by the way. In the two classes next week, so Monday and Wednesday, we'll probably just go through 3.3, which will start now. And it won't be on the exam, but we'll cover 3.3, and then the exam will be Friday. But 3.3 is, of course, stuff you're familiar with, stuff you know. We postulated the SAS congruence condition. It's one of our axioms. We just say we're going to accept this as a fundamental truth. But then we have all these other congruence conditions. And it turns out in neutral geometry, all of the congruence conditions that you know for Euclidean geometry are still true. So from SAS, we still have ASA, we've got SSS, and so on. And I think they're worth proving. If you remember back in Geometry 1, we didn't actually prove them. We just said, remember, you have all this stuff from high school geometry, we're just going to accept them all. But we didn't prove any of them, so let's prove some of these. So the first one is ASA. And it says a bunch of words to make this very precise, but you know what ASA means. So if the vertices of two triangles are in a one-to-one correspondence such that two angles and the included side of one triangle, two angles and the included side of one triangle are congruent to two angles and the included side of the second triangle then the triangles are congruent. And so I have a bijection between these two triangles. I have a bijection that maps vertices to vertices, sides to sides. And if I can do this bijection in such a way that two angles are the same and the sides between them are the same, then they're congruent. In other words, a triangle is uniquely determined by just knowing an angle, and a side length. If you know that, then you know the triangle uniquely. You know this angle, and you know these other side lengths. Why didn't we prove these in Geometry 1? Because the proofs are fairly long, and there's a whole bunch of these congruence conditions. But obviously here, we're going to invoke SAS to prove this, right? We've got our one axiom SAS. Let's use that to try and prove these other ones. So we'll start with two triangles. So I've got a triangle ABC, ABC, and I've got a triangle DEF, DEF. Okay, so let's let triangle ABC and triangle DEF be such that angle BAC is congruent to angle EDF, angle ABC is congruent to angle DEF, and AB is the same length or congruent to DE. Alright, so what are we assuming here? BAC, what angle is that? BAC, I've assumed that this angle is congruent to EDF, this angle. I've also assumed that ABC, what angle is this? That's this angle. ABC is congruent to DEF, this. And I've assumed that AB is congruent to DE. So there's the assumptions of ASA, right? There's the hypotheses. What do I want to do? I want to show that these must now be congruent triangles, right? Well, if I want to invoke SAS to show they're congruent, then what do I need to show? I need to show that I can do either one of these. If I can show AC is the same length as DF, we'd be done, right? We'd have ASA. Or if I can show that BC is congruent to EF, if they're the same length, then once again I can invoke, did I say ASA? I can invoke SAS, right? In either case. So if either AC is congruent to DE or BC is congruent to EF, then the triangles are congruent by by SAS. So let's suppose they're not. Suppose they're not the same length, and let's try to reach a contradiction. So suppose that AC is not congruent to DE.
Don't you mean DF?
DF, yes. Have I done this twice? Yeah.
AC and DF, yeah.
DF. DF and DF here. Thank you. DF. If they're not congruent, what does that mean? It means they're different lengths, right? One has to be longer than the other. If they're different lengths, one of them is the longer one. So let's assume without loss of generality that AC is the longer one. If they're not, just relabel everything so that AC is the triangle with the longer side. So, and without loss of generality, assume that AC is the longer side. Well, what does that mean? That means I can come in here, I can come into AC, and I can choose a point that we'll call C prime. So that AC prime is the same length as DF. Alright, so let's, since AC is bigger than DF, there exists a point C prime such that C prime is between A and C and collinear with them, and such that AC prime is the same length. Actually, again, let's not talk about lengths, let's talk about congruence. Is congruent to DF. So I built this smaller triangle inside of this guy. And I built it so that this side AC prime is the same length as DF. What can I conclude? Now I can use SAS, right? I can use SAS. This side is the same as this side. This angle is the same as this angle. This side is the same as this side. So AC prime B, or ABC prime, must be congruent to DEF by SAS. So by SAS, we have that this triangle ABC prime is congruent to this triangle DEF. Can I erase? Okay. Well, now let's make some observations about what the measures of these angles have to be in this case, because the contradiction is coming. Right, so therefore, the measure of angle ABC prime, that is the measure of angle DEF. Right? this angle here, ABC prime, if these are congruent, then this angle, I'm gonna put 3 lines on, has to be the same length as this guy. Or sorry, the same measure as that guy, because they're congruent triangles. But we've already assumed for starters that angle ABC is the same as angle DEF. So just by our original assumption, this is the same as the measure of angle ABC. This is the original assumption. Meanwhile, this equality is by the congruence. The congruence we just established. And the contradiction here is obvious, right? In this picture, this angle cannot be the same as this obviously larger angle. Right? It directly conflicts, I believe it's the angle construction axiom from SMSG, it's number 12, that says if I want to construct an angle, there's a unique way to do it. So I can't have 2 different rays coming out that construct the same angle. So this is a contradiction. This contradicts the angle construction. Axiom. This is SMSG number 12. You guys do see the contradiction, right? It's, again, the angle construction axiom says, you give me an angle that I want to build on this side AB, there's a unique ray that does it. I can't have 2 different rays that build the same angle. Okay, so what's the conclusion? How do we get this contradiction? We got this contradiction by assuming that AC was not the same length as DF. Well, now it is, now it must be. So, hence, AC is congruent to DF. And as we agreed to start with, that's enough. Once I have one of those sides, AC is the same length as side DF, then by SAS, we have congruence. So, triangle ABC is indeed congruent to triangle DEF, as we wanted to show. Sort of a fun proof. We'll go through the others. SSS in particular takes a bit of work. We're going to prove sort of a lemma before we do that. It's the hinge lemma or the hinge theorem. So some of these aren't easy to establish, but we'll go through them, and we'll do that next week. So in the meantime, see you guys. If you're studying for the exam, which you should be, there will be questions on the exam where I just ask you to state definitions, right? Define this or state this theorem or whatever. There will definitely be questions where I say, here's some axioms, here's an axiomatic system, build a model for it. So all the types of things we've been doing this semester so far.
So maybe this is. Yeah. Yes, okay, that